Leah, behind you.
Oh, you asked me what I've been doing. I've been doing a lot of drawing at night. So I was drawing at night to get a thesis cover. I'll show you actually, Jen. So the one on the, I've got a lot, like quite a lot. So when I did my PhD, I did a hard copy.
Oh, wow.
So it's actually not out my window. I can see it out my window. I did it outside. So what I've been doing is I've got like a lot of drawings of darkness and a lot of drawings of like, you know, where the land and the sky meet and what you can see like in the darkness. And because I'm up here, like I'm on the edge of the southwest, it seems the logical thing to be drawing. So that's what I've been doing.
That would be a cool exhibit.
Yeah, it's great. It's been great fun. I mean, it was great doing it for that thesis. just draw a cover for the thesis was really fun.
An exhibit of the dark. Really
yeah.
Cool. I mean, it'd be really neat.
Yeah, lots of fun.
Thanks for showing up, guys. Really glad to see everyone getting used to this.
Is John here?
Who?
John.
Yeah.
John is not here. There's another meeting that will be happening in our Mars Society Australia, so he's probably prepping for that.
He's prepping for that. I was just talking to him, and I'll be leaving 20 minutes in to go to that meeting.
Okay.
Yeah. Somehow we had a clash of meetings. I think it's not an AGM, is it, Sid? I don't think so.
No, it's not an AGM, but he's prepared a report for the board.
Yeah.
Okay, Sid, it's time to let everybody in.
Okay. People have already, I think, started getting in. We can
77, 28. Okay, yes. Sorry, yeah.
So, Afshin, did you...
Yes, do you want me to take over?
Absolutely, go for it.
All right, so good morning, everyone, and wherever you are in the world, appropriate timing according to your time zone. Welcome to our class today. Also, I have the pleasure of introducing Dr. Siddharth Pandey for his talk. So Dr. Siddharth Pandey, as you know, he is the head of the Center of Excellence in Astrobiology at Amity University in India. This is where he did his undergrad in, he did a BTech in aerospace engineering, and then he went on to do a master's in space systems engineering from TU Delft in the Netherlands. And finally, he did a PhD in aerospace engineering from the University of New South Wales in Australia. He is actually spearheading this effort to initiate India's first dedicated Center of Astrobiology and Space Biology research in the country. And as we can see, he's doing an amazing job at that. He is a very accomplished space engineer with project management and leadership experience working with teams of astrobiologists around the world. And prior to his experience at Amity University, he has work experience building sample collection instruments for Mars and Venus sample surface missions while he worked at NASA Ames in the US. He has been engaged in education and public outreach activities, and he's very motivated to use space as a tool to spread awareness, social consciousness, and inclusiveness within our communities. So with that, I will hand over the stage to Dr. Siddharth to enlighten us about space missions.
Thank you so much, Afshin, for that more than generous and kind introduction. Welcome, everybody. Welcome to our 5th class. And I will be talking to you about the different missions that have been held, the ones that are currently ongoing, and the ones that are in the pipeline. And let me just try to quickly share my screen. Okay. Afshin, can you confirm if my screen is visible?
Yes.
Okay, thank you. Right. So what I will do is my task for this class is to not give you a complete digest of all the missions. Okay, it's not going to happen. It's we've had quite a few missions. The idea is to just pull out some of these questions and see if we can do some justice to them in the form of an introduction, right? Because it's an introductory course, we have to keep ourselves away from the temptation of diving deep and getting into each of these topics. But at the same time, it's important to cover as many unique aspects that astrobiology brings to missions. So with that, I have postulated these questions that hopefully I will address to a certain degree of depth. What are astrobiology missions? That's the first question. What differentiates a regular planetary science mission from an astrobiology mission? What are the unique challenges that are faced by them? And I'll talk about the different challenges, both from an instrument perspective, a system perspective, or a mission perspective. And lastly, how do these results that we are finding on Earth or on previous missions, how are they shaping the future missions? So I'll be touching a bit on that, not too much, but a little bit about that. And I really recommend all of you to check out this cool webpage, that the NASA Astrobiology program website has, that gives you a more comprehensive list of missions if you're interested in going through all of them. So in the interest of time, that's a link that will be there, and these slides will be up on the classroom drive as well, so you can all have a look at that. So what exactly is an astrobiology mission? What are we looking for? When you hear the word life detection, when you hear the word biological signature detection, what is it exactly that you're looking for? So it can be, according to one definition, it can be classified as looking for ingredients. So finding the elements, the molecules that are necessary, the precursors that would really be needed in place for the biology to happen. And then the other things are the byproducts. So the most obvious thing obviously is that you're looking for actual biological activity, or for that matter, biological organisms. But it's not just that. Even things like complex organic matter that is on Earth normally found to have been produced, it requires a lot of biology, or it requires a certain amount of biology for its production. That complex organic matter also gets classified as a biological signature. So these are just some very loose, broad definitions of what exactly is it that we're looking for. And of course, we've had Dr. Michael Macy and Dr. Jen talk about, and also Dr. Afshin talk about this in detail in their lectures. But this is primarily the targets that these missions have. And if they're looking for any of these things, they get classified as astrobiology missions. And you could also classify these signatures as either chemical signatures. So if you're looking at some of the elements, you're looking at the bulk mineral chemistry, you're looking at, like I mentioned, some of these essential elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and things like that. Or you're looking at morphological signatures. So you're really looking at the textures, you're looking at the surface textures from a distance. You're trying to understand if you can make out any microfossils in them, or any kinds of alterations in them, or even looking at, like I mentioned, some of the byproducts that have formed. So you're not really chemically analyzing them, but you're just taking the images and you're looking at them. So, and then these are normally in the form of cameras, all the way from ultraviolet to infrared. And this is, of course, there's several other techniques, but I'm just trying to focus on some of the most commonly used instruments that are normally integrated into missions for astrobiology. And this, of course, this analysis is normally done, you can say, in 4 different ways. So one is remote sensing. So you have orbiters and flybys, which basically, once you're around your particular target world, it could be a moon, it could be a planet, you're observing it from a distance. The second way is, of course, you're landing on the surface. So you're doing a lot of onboard analysis where you're collecting samples with a drill or a scoop, and then slowly bringing it inside the rover or a lander, and then conducting the experiment inside. It could also be an onboard analysis. For example, if you don't even need to be on the surface of a particular planet or a moon. You could be flying through the plume that is coming off a particular icy moon. And there could be instruments on board which are actually doing the analysis. And some of it was, for example, was done on Cassini. So that classifies itself as an onboard analysis of samples, collected samples. And the last one is laboratory analysis, which is, of course, the most ideal. which basically is when you're collecting the samples and then there's a sample return mission. So you bring them back to Earth and then you do all of the analysis in a state-of-the-art laboratory that is obviously very challenging to replicate on the surface of Mars, because most of these instruments are quite large, they're bulky, and you can get, you have samples, you can share them with different labs in different parts of the world and do those kinds of analysis, as is normally done with the sample return missions. Like Apollo was one. It wasn't an astrobiology mission, but then there's also Stardust and some of these other missions which actually brought back the samples. And Hayabusa 2, in fact, which I'll be talking about a little bit, is also planning to bring back samples in a few months, in fact. So those are ideal astrobiology missions because you can actually break down some of these questions that I'll also be talking about that are asked, and some of these criteria that need to be fulfilled to have a successful biosignature measurement. So very quickly, for those of you who are perhaps not completely familiar with what we mean by an orbital mission or a flyby mission. So a flyby mission basically leaves Earth. It uses the gravity of the different planets or moons to kind of slingshot its way around it. So as you would know in space, gravity is a very significant field, especially when you're moving at these very, very high velocities towards objects. You tend to leave the gravitational influence, sphere of influence of one planet, which is, for example, Earth, where you're starting from. And then when you're supposed shooting towards Mars, you could do a flyby mission wherein you don't really enter the orbit of that particular planet, but you're just kind of carefully maneuvering around it, that you do a pass, you're able to come very close to it, do certain measurements, and then get away from it. So this, in many ways, saves a lot of fuel. Trying to place yourself in a particular orbit uses a lot of fuel. And that fuel basically means that you have to compensate carrying as much fuel, and therefore the size of your instruments also reduces. So we've seen several different kinds of flyby missions, and Voyager, in fact, was one of the most popular and successful ones at the start. There's also Pioneer. And then we've had missions like Galileo, Cassini, Huygens, New Horizons, and Hayabusa. And all of these missions and many more have actually done flybys of several different worlds. And while they've done these flybys, they've been able to take certain measurements or certain images while they were doing that. And that's obviously a very, very important thing, especially in the case of Cassini, where it was actually able to go around so many different kinds of moons and planets, Jupiter and Saturn, and it spent time around the icy moon Enceladus as well. So that's one kind of missions. And then the second is obviously orbiter missions, where you place yourself, for example, in a polar orbit, in a reasonable orbital velocity. So you're able to fly slow and low as compared to a flyby mission, which is pretty much a single shot or a double shot, depending on what the mission profile is like. So orbiters like Maven, Rosetta, which was around a comet, and the planned Europa Clipper mission as well. These missions have dedicated orbital time, so they'll be spending time. And just like on Earth, we have a lot of satellites that are in our orbit, whether that could be low Earth orbit or geostationary orbit. They all have different kinds of roles to play, and each orbit obviously allows you different kinds of capabilities. So if you're on a polar orbit, you're able to cover a lot more ground, a lot more space, and also over time you can actually see what kinds of differences are taking place. And thirdly, of course, is the most exciting form of an astrobiology mission, is where you're actually going to land onto the surface. This again obviously depends on what exactly are you landing on. Are you landing on an airless body like a moon, where there is no atmosphere to kind of break you? Because obviously you have to understand that you are traveling from Earth or from whichever body you're slung short around, and you're coming towards your target planet or your target moon at a very, very high velocity. So the reason these missions are expensive, they take time to build, and are technically challenging, is because it is very, very difficult to firstly, slow down. So there are a series of automated braking events that are normally held. Like even landing on our own moon, which we would expect to be, right next to us, just 4 days away from us in terms of flight, is also something that is not completely, you can say championed. There've been the Israeli mission that landed and crash landed on the surface. The Chandrayaan-2 lander as well had the same fate. you basically have thrusters on your vehicle that tend to fire in the opposite direction, because in space, there's nothing to press against, right? So when you're saying braking, the only way you can slow down is if you reverse thrust. You fire your thrusters in the opposite direction, and that kind of reduces your kinetic energy as you're moving towards an object, right? And it becomes slightly more difficult when you're doing it when there is no atmosphere to give you that friction to slow down. In the case of Mars, obviously, yes, there is the atmosphere. It's about 1% of our own Earth's atmosphere, so it's not very thick. And you're coming with a much higher velocity as you're moving away, you're moving towards Mars. So that's why soft landing on the surface of Mars has been one of the most challenging things that have been achieved. And we've had many failures. And we've obviously now achieved with the 2, 3, 4 different surface missions, orbiter, rover, as well as lander missions. But landing on the surface gives you a lot more opportunities. Once you're on the surface, you're able to do, your capabilities increase. You're able to touch the samples, feel the samples. You're a lot closer to your target rock, whatever you're looking at, and also looking at the surface atmosphere. So we've had missions like the Viking, Curiosity, Perseverance, and ExoMars, which have been surface missions that have answered, astrobiology relevant questions to some extent or the other. And then, of course, there's missions that are telescopes, so space telescopes. And in this talk, I will not be having the time to cover those, but I should mention Kepler and K2 mission, which in fact has been one of the most successful, space telescope missions that we've ever had, that have identified and characterized planets and their habitability. Over 4,000 planets that have been identified. So these are, in general sense, all the different kinds of missions and how exactly they take place. And depending on what your target is, you can actually plan out your mission accordingly. I will not be talking also about missions that are held on the International Space Station, but I also did want to acknowledge that there have been several very important space biological experiments that have been held on the International Space Station, where we've actually carried some very critical organisms that we find here on Earth that survive in extreme environments, and we've exposed them in microgravity. So for example, the Expose-E mission that was flown on the International Space Station. I've also put in our own little experiment, which hasn't seen the space environment yet, but is also trying to understand how does a plant sample, plant callus actually grow in microgravity environment. And then, of course, you can do astrobiology missions on the International Space Station. You can also do space biology missions. The difference between these two is space biology is mainly focused towards improving improving lives of humans in space. So if we need to understand what are the long duration effects of spaceflight on us in terms of the radiation, the reduced gravity. So we basically study that on different organisms, and all of that comes under the domain of space biology. But astrobiology is, of course, much larger than that. It's not just about humans, it's about understanding how did life originate, can it survive outside of Earth, and what are the possibilities of us finding it elsewhere. So it's a much larger question. And there have been a series of experiments that have been held on Skylab, space shuttle, as well as on the International Space Station. So that's another domain that I will not get into. I want to only focus on missions that have been looking for life. So this is a criteria sheet that has been identified. I have left the link of this paper by Mark Neveu and all in astrobiology that came out a couple of years back. They are basically trying to build a life ladder experiment where they're trying to identify, based on the knowledge of the previous missions, they're trying to come up with some kind of criteria that helps teams define astrobiology missions. And one table that I really found interesting, from that particular paper that I've brought out here, are these different criteria that have been kind of put in place that can help us determine with the required amount of confidence whether what we're looking at is representative of biological activity or not. So the first 3 points, so the sensitivity of the instrument, it needs to, the limit of detection, the limit of quantitativeness that you're actually trying to measure of whatever the target sample that you're after, it has to have a certain amount of sensitivity. And that's something that is achievable, obviously, because you can test that on Earth. You can see at what concentration levels, down to either parts per million or even parts per billion, you're able to actually capture and measure whatever element that you're looking for, or molecule that you're looking for. The second is contamination free. So obviously you want to ensure that your instruments are sterilized. They're not having any form of earth-based organisms around them, or even any kind of earth-based gaseous effects. Any kinds of external influences should not be there in place. So that comes under contamination free. And obviously repeatability. You want to have at least 3 independent measurements of the same particular experiment to take place, to have enough data to be able to have a statistical analysis to say that what you're finding. And I also mentioned the NASA Viking Mars lander, and I have a slide on that. This is an important mission for those of you who are interested in astrobiology missions, because it was the first ever mission that was primarily sent to search for life. So that was the importance of this particular mission. This was the heights, or the glorious space age, right after the Apollo missions. We were looking at Mars. This was this nice, you can see Carl Sagan standing there with the mock-up of the Mars lander. And that was the size of that lander that was sent up, so many years back. And it obviously gave some results, but many of those were unfortunately not completely, conclusive of biological activity. And at that point of time, obviously, these criteria were not in place. So many of these things have actually been developed as our advancements have taken place in terms of our micro analysis of samples, looking at microscopy, also the molecular biology techniques and assays that have improved over the last 15 to 20 years or so. We've gotten better at miniaturizing our instruments, our techniques in which we can sterilize our instruments, and also our understanding of life on Earth as well has improved. Looking at some of the oldest living forms that have been found, analyzing some of the samples, not even from Mars, but from Earth, and trying to use this particular criteria sheet against those samples. We've always come to the understanding that it is not a very straightforward process. And the more we've understood that problem, it's improved our ability to design these specific missions. So the Viking Mars landers were equipped to handle the first 3 points in that criteria sheet. And they were supposed to test for 4, 5, 6, and 7, where they had to make sure that they're able to detect a certain amount of concentration, preservation potential. You should be able to, whatever sample you're analyzing, you should be able to preserve it. It should not be affected by any external influences while that test is happening. Reliability, it should be compatible with Earth life. Now, this is something which can also be a hindrance, where supposing you're encountering a form of life that is not Earth-like. So it's something that would be unusual. It can be recorded, but that kind of goes against your drive to determine if it's biological or not, because we don't have anything to compare it with. The only thing we have something to compare it with is Earth life. So that's why it becomes important to have that point there to be able to, have a certain amount of robustness in the measurements that are coming into place. And also lastly, and this became an important point, especially when a lot of debates were taking place with the results that were coming back and all of the findings that were coming out, is that the biological interpretation must be the last resort hypothesis. So it should be something, the burden of responsibility to rule out all of the abiological origins, the potential abiological origins is on the person who's doing this analysis. So this is just a snapshot of the table from that particular paper. I've just put it in here to just kind of reiterate. And I'd really like all the participants to actually go through this paper. It's a very nice paper. And they've listed out the different criteria like I just spoke about. They've given an explanation in the second column. And in the third column, there's a short note as well, where they've tried to explain the different ways in which these criteria can be met. So I encourage everybody to go through that in detail. And I'll also talk a little bit about the different missions down the line to show where we were successful and where we were not successful. And between that shortcoming and the findings lies the challenges. So I think that will be something that I hope the participants are able to take back from this particular lecture. So talking broadly about the unique challenges that are faced by astrobiology missions, many of these are, not just because they're astrobiology missions, but because they're venturing out into outer space. So the first being the policy related. So right now there are planetary protection guidelines for instruments, the way they are built, the way they need to be calibrated and qualified, as well as eventually assembled and integrated. And then the final testing takes place of the entire assembled hardware. And we have a lecture happening next week on planetary protection, so I will not be getting into that. But just to say that planetary protection ensures that you're not taking with you any Earth-based organisms, or even any kinds of, some of those ingredients or byproducts, like I mentioned, any of those Earth-based biosignatures along with you. So you want to ensure that you're meeting a certain, certain level of cleanliness while you're doing it. And it's even more stringent when you're visiting a particular planet or a moon, which has been classified as important for, studying whether there is life there or not, or whether we can, take life from Earth there or not. For example, Mars, Enceladus, Europa, these are obviously the highest rated destinations, and the amount of requirements for these particular areas is obviously very, very high, as compared to a place like the moon, where it's quite less. It's one of the least, you can say, stringent in terms of the guideline criteria in place, because we do have a strong reason to believe that there is no life there, and we can send things. So that's the policy related challenge. The second challenge is environment, and this is obviously where my personal you can say role comes in, where I'm particularly a person who has a background in thermal modeling and also pressure. So when you're trying to land on a surface that is either further away from the sun, or if it's closer to the sun, for example Venus, you have all of these different kinds of environment-based challenges that start affecting your the operation of that particular spacecraft. So whether it is a flyby or an orbiter or a surface instrument, or even the instruments. So they start, you want to ensure that all of these external parameters are not affecting your readings. And this is normally done as much as possible by passive means. So you have passive thermal insulation, for example, that tries to ensure that your temperature sensitive instrumentation, and mostly it is the cameras or the batteries, are protected. You want to ensure that they don't get damaged because of that high or low temperatures. For example, if you look at Mars, you're landing on a surface which could be anywhere between -70 degrees Celsius to -5 or +5 degrees Celsius. And then Mars is obviously a planet. It has day-night temperature variations. It also has seasonal temperature variations. And when the Mars Science Laboratory, when it landed on the surface of Mars, it was normally operating in the thermal system was operating on two modes, which was mainly summer and winter. And the entire thermal management system has to be automated. And I'll talk about why that is important, the importance of automation on these missions. It's because you're so far away from Earth. So any form of communication that you're having to either start something or stop a particular system takes a lot of time. In the case of Mars, it can take about 20 minutes each way to send a signal. So before you would even know it, a lot of the systems would be damaged. So it's important for the system to have that level of independence to be able to heat up or cool down based on the temperature that it is facing. But even more so, in an environment which has a slight atmosphere like Mars, even if it's a light atmosphere, it so turned out for the Curiosity rover that it wasn't just the summer mode and winter mode. There's actually a spring and autumn mode as well, which was not completely built in. And the engineers realized, and there's always a team of at least 50 engineers at any given point of time that are active on a particular rover. With the data that was coming back to them, they very quickly realized that their system was either undercompensating or overcompensating for the amount of heat it had to actually release or not release to keep its system warm. By that I mean that in summer it was releasing more energy and wasting that energy when in fact it didn't really need that much. And in winter it was not doing as much. So there was these constant tweaks that had to be done over years to ensure that we were able to completely understand that temperature. And it becomes even more complicated because the Martian surface has, even if it's a 1% of our atmosphere, it does have gas. and that gas can lead to convection. And my personal PhD area was actually trying to understand that what role the thermal convection around the rover or even inside some of the rover's components can play in terms of some of the heat losses that take place. Pressure, yes, you want your systems to be vacuum sealed, to be completely insulated to ensure that there is no interaction. In certain cases, they are vented. By vented, I mean that it's not completely sealed to actually allow, the planetary atmosphere or the moon's atmosphere to enter in and out, depending on what exactly you're doing. Especially for cases where you're drilling for a particular sample and then you're bringing that sample inside for analysis, where it has to undergo some form of either a spectroscopy analysis, or you're adding a particular substrate to it and then seeing what comes out of it and doing a gas detection. In those cases, you have to open up to the atmosphere. So how does that pressure affect you? And pressure actually makes it even worse now that Venus is the hot topic. Everyone's talking about, trying to understand if there's life on Venus. So that is a completely dense environment that you're trying to enter. Even Titan, for that matter, is having these dense hydrocarbon clouds all around it. So all of those things, become important in terms of understanding. Radiation, of course, that's always a challenge. You have galactic cosmic radiation coming from the universe, and then from the sun, you have these solar energetic particles. And this becomes important for us to understand what effect do they have on the operations of your particular system. Are they affecting your onboard or your field analysis in any form of way? Is there a seasonal variation in these radiation outbursts that happen, like a solar outburst that happens? How does that affect your instrument, and how does it affect the entire environment around it? So that's another parameter, and you'll often find radiation measurement systems that are placed on rovers that tend to do this. And Curiosity, in fact, showed quite high levels of radiation, and that radiation monitoring was important. Even on the 2020 Mars rover Perseverance, there's going to be a radiation measurement device that will be constantly measuring the radiation while the rover is going about its activities. And that's not just important for the experiment by itself, but also for future missions that involve perhaps humans on the surface. So it becomes even more important to understand how much radiation protection do we need, what parts of the systems need to be protected. And lastly, mechanical stresses. Now, you must understand, launching from Earth, getting into space, you have to go through a rigorous amount of vibrations because you're sitting on top of a very strong, heavy rocket that has to push against the Earth's gravity, put you into Earth orbit. And that requires your system to be fairly robust structurally. The vibrations should not cause any form of resonance that can kind of break down your system from inside. So all of these systems, as it is, go through anything that you send to space has to go through a certain amount of vibration analysis. But it becomes even more critical for astrobiology missions, where you're flying these really sensitive instruments, these cameras, these miniaturized spectrometers, these different kinds of systems that have to, that are a lot more sensitive to any form of mechanical stress. And a mechanical stress can be, in fact, even induced by temperature, where obviously if there's anything metallic, it will expand or contract based on the temperature that it is in. When you're trying to land on the surface, when you're trying to do a soft landing, you're obviously, even before that, in fact, when you're approaching the particular target world that you're interested in, you're doing this braking, like I mentioned. So all of these different things, you want to ensure that your system is completely robust in the ability to, handle some of these stresses as you come by. And obviously there's these mission related challenges, and these are not just unique for astrobiology missions, but like I mentioned, anything that is going out into the outer space. These missions are expensive. They are an order higher, at least, than regular space experiments that are conducted, for example, in low Earth orbit or even to the moon. The further you want to go away, the more fuel you need. The more fuel you need, the larger rocket you need. And that exponentially brings up the cost of these missions. The amount of time that mission will, the spacecraft will take to reach the particular destination can almost be up to 10 years, a decade. And that means you have to keep a full team of scientists and engineers employed for that duration of time. So all of those costs, are even adding to your mission. When you're trying to build a mission to Jupiter or Saturn, you have to ensure that you have a team that's constantly employed and working on these different things. And even before that, in fact, the level of testing and qualification that is done for these missions takes up a lot of time on shared facilities that you're using for doing these testing, and all of that adds to the cost. Coming to obviously the mass, the volume and power, like I mentioned, the further you want to go away, you have to carry more fuel, and that in many ways limits the size of the payload that you're sending, the mass of the payload, especially if you're trying to land on the surface of another planet or moon. You want to ensure that the amount of braking that you need to do is less, because the heavier you are, the more braking you will need to do to slow down. So all of those factors play in. And on most occasions, except if you're going to Venus, on most occasions, you'll be heading, if you're looking at the solar system, you'll be heading away from the sun. So which basically means that you will not be having a lot of solar energy to work with, because anything beyond Mars, you cannot rely only on solar energy. So you need to have a decent amount of power budget to be able to handle that. So whether that is radioactively powered, radiothermally powered, that is, or you're just solar electric. So that will also determine the rate at which the velocity with which your mission will be traveling, and also how fast you can get there or not. So that's why you see a lot of these missions have these flybys where they're actually using the gravity of the different orbiting bodies to kind of slingshot themselves towards a particular destination. And these are these smart and unique ways in which you can actually, so you never really launch from, if you want to go to Saturn, you don't always just launch. You don't launch up from your launch site here on Earth, get into orbit, and then immediately just straight away shoot for that particular body. Well, you can do that for Mars, but if you're heading anywhere further away, you have to go through these different flybys to be able to get that energy to get to those particular areas. Heard of an average scientist's career span. So many people, in fact, have started, being part of expeditions such as Cassini when they were just graduate students. So some of you right now, you might be involved in a planning of a particular mission right now, and it's only by the time you're retiring, you'll actually see, or maybe even slightly before that, you'll be actually seeing data coming out of it. So it can get a bit depressing to think about it like that, but that is the truth. I mean, these worlds are not close to us, and it takes time to develop, missions, and especially the icy moon missions, the ones that are heading, further away. And also there are a lot of specific challenges which are operation of the instrument related. So in addition to the table that I presented earlier, which as it is makes it harder to determine whether the signal that you're looking for is biological or not, there are also some of these other capabilities that you would like to have. For example, you might find some signals that you are able to receive, but you're not able to completely, the system is not able to interpret. So it needs to have a certain ability to be able to capture those signals. And there might be something that are different from what it had been designed for, which is exactly what it's doing. It's looking in the unknown. So the level of uncertainty in what it will be receiving is higher than other missions that are having, I would say, relatively more constrained boundaries in terms of what they're looking for. And non-destructive analysis techniques as well. On many occasions, you want to ensure that when you're doing the analysis, you're breaking down it in a way, so either you are completing the entire analysis on that particular planet and sending back data, but on many occasions now, we're also looking at collecting the samples and then storing them for a future mission to bring them back, which is what the NASA Mars 2020 rover mission will be doing. It will be actually collecting and caching and storing these instruments. So that again becomes a unique challenge, because there are several different challenges associated with drilling as well. And I'll talk a little bit about that. So very quickly, let's see how am I doing on time. Okay, I'll try to get through these missions. I will not go into detail because a lot of this information is already out there, and there's textbooks and websites that will do more justice to the topic than I would. But I just wanted to highlight some of the important learnings. These we can use these as stepping stones working towards future astrobiology missions. So the Viking mission, right? Like I mentioned, it was the first ever mission that was supposed to be looking for life. It had primarily 3 experiments. They were substrate addition experiments that were looking at trying to understand whether there's any form of biological activity or not. Unfortunately, these experiments were not, you can say, comprehensive in terms of their ability to confidently confirm that whatever they're finding, they were not able to rule out whether the source could be abiotic or not. When I say abiotic, it means that it has been formed because of a regular, you can say, chemical formation, and there's no biology involved there. So they were collecting samples. They were either humidifying them based on the gas exchange experiment. In terms of the LR, the label release experiment, you were adding a certain amount of carbon and then trying to monitor if there's any form of carbon dioxide or methane that is being released, which would indicate if there's any form of microbes in the soil, or they were in fact even heating the soil, which was in the pyrolytic release experiment. But they weren't able to confirm any form of organics in the soil. In fact, they found perchlorate, which was a dampener, because people realized that if there's perchlorate in the soil, then most likely life has already been destroyed, even if it was there, because perchlorate, as we know, is toxic towards organic life as we know it. But they were only obviously scraping the surface. So there were several different limitations in terms of how this experiment was conducted. But even the fact that it did not find anything, it did 2 things. One is, from a general consensus standpoint, Mars exploration did suffer. There weren't any follow-up substantive experiments in the next 10 years from that, 10 to 20 years from that, from the Viking mission. But it actually not finding something or an inconclusive result also actually opened up another series of questions that that needed to be answered. And then, of course, I'll jump to the Mars Science Laboratory, but this wasn't the immediate mission after this. They were obviously the Sojourner rover, they were the Mars exploration rovers that came after it. But I'd like to highlight the fact that the Mars Science Laboratory was the first mission that confirmed that there was flowing water. There were the presence of organics. They found clay at some of these particular sites. And this was confirmed by different kinds of instruments. So in terms of spectrometers, it had the APXS, the ChemCam, SAM, Chemin. In fact, Dr. Jen, who's on the call right now, she has been a scientist on this particular rover team. So she'll know about all of these different experiments that came out, some of these results that came out. And obviously it had this very neat imaging system, and a system that was able to remotely shoot a laser and basically obliterate a little bit of rock that it's looking at. And based on the gases that escaped from that particular laser impact, it was able to actually analyze from a distance what are the concentrations like. So it was, I think, one of the most complicated machine that ever landed on another body. And it did its task. It's still doing its task. It's an active ongoing mission. And it actually answered some of these questions that inspired and empowered NASA to go ahead with the sanctioning as well as the development. And now recently we have seen the launch of the Perseverance rover. So this rover, in terms of its actual structure, it's similar to the Curiosity rover, but it's doing a lot more. It's going a step ahead. It has, you can say, the next generation or the next iteration of instruments in terms of the spectrometers. It has an X-ray spectrometer. It has a UV Sherlock spectrometer. In terms of imaging, of course, it has the similar mast cam that you're seeing on the hardware. And it also has this technology demonstration where it's actually flying a helicopter. The first time ever we will have an aircraft, because helicopters classify as aircraft, flying on a different world. So I think that is really, really exciting. And it has its task set. It is landing on the rim of a crater, the Zero crater, and it will be looking for signs of present or past life, signs of biological activity. In terms of technology, it will be collecting and caching these samples, so storing these samples for a future mission for sample return. And like I mentioned, the helicopter flight demonstration. So for the first time, inside the surface atmosphere, we will have an object that will actually be flying very close to the surface and flying around. So it's able to actually, it'll be a 90-second flight, I think. And within that duration, it will be just achieving certain engineering tasks. So it's not having a science instrument on it, but the ability to do that in a Mars atmosphere, I think, is tremendous, because the Mars atmosphere, like I mentioned, it's a lot thinner. So you don't have enough air to kind of push yourself for the helicopter blades to push themselves down to, which is why you see these really large blades. And all of these things were developed at NASA JPL. And I think it will be a massive win for the, you can say, the engineering community who are interested in Mars exploration if they're able to pull this off. And I'd also like to mention that our team, I think it's been brought up previously, had visited a crater site in India. It is called Lonar Crater. It's in central India. And it is similar to the crater where this particular rover is going to. It's similar in the way that it is formed in a volcanic province. It's inside basalt. So there are, in fact, just 2 or 3 such basalt crater impact sites that are still well preserved on our planet. But we have many of those on Mars. And the reason Jezero is landing in this particular crater is because it's landing close to that delta. You can see on the lower right side, you have this ancient inflow that you can find that many years ago, you had deposition of organics that were flowing in from, now that we've confirmed that there was flowing water in the past, we expect to find sedimental deposits over time. And we see that in Lonar. We have a lake that is existing today. So we're not so much interested in the microbial ecology of the lake inside the crater, but we're interested in the geology of the crater, the morphology of how it has formed over time, and its ability to actually preserve any form of ancient life inside the cracks of the gullies, in the delta, as well as the outer ejecta. So we had made 2 trips last year, and hopefully when things improve, we'll be heading back and testing out certain drone-based systems to be able to do habitability studies based on some of those biosignature measurements that I spoke about. So probably hyperspectral analysis, which is integrated onto a drone, a hyperspectral camera, and trying to see the effectiveness of these systems in helping, you can say, tick off some of these questions that are being posed, and basically improving future technologies for crater-based, exploration. There's also the European rover called Rosalind Franklin 2022 rover mission. So this mission got postponed, unfortunately, due to the COVID lockdown. It was supposed to fly with Perseverance this year itself, but it's also a very ambitious rover. It's also an astrobiology mission. It has many different kinds of instruments. I will not go into all of them, but these are just some of the critical ones that I pulled out. It has its suite of spectrometers going from neutron spectrometers, infrared, GCMS. It also has a drill, which is extremely exciting for me because I'm excited about drills, and I've been part of a couple of projects where we were actually developing drills for planetary missions. And this drill, in fact, is going to be drilling up to 2 meters, which is actually something that has never been achieved before. Even the Curiosity rover that launched in 2012 has only been able to achieve a few inches of drilling. And why does it become more and more challenging when you're trying to achieve this depth? It's because the further you drill, the longer your machine is engaged, the chances of things going wrong increase. That is the first thing from an operation standpoint. From a geological standpoint, you can never be sure as to, eventually you always expect to find a certain kind of geology, a stratigraphy layer when you're drilling through, and you would expect to know what exactly is it that you're drilling through. But for most of these missions, even though with Mars, we have, I think, the relatively as compared to some of the other planets or moons, we have a fairly good understanding of what we might find. But as soon as you start going below the first few tens of centimeters, you're in many ways in unknown territory. It could be anything from loose, finely grained regolith to something that's really hard, rocky, or if it is actually ending up landing somewhere where there is ice involved, you might even encounter subsurface water ice that is kind of infused in the minerals. And these are challenging things to drill through. And to have a drill that is kind of an all-in-one that can do all of these things is never a possibility. Drills are specifically built for certain kinds of materials to drill through. And also you're doing this drilling in a low Earth, in a low gravity environment. Mars has 1/3 of gravity as Earth. So you must understand that if you're drilling, there has to be something that you're pushing against to kind of go down. And normally, with these rovers, it actually uses the weight of the rover It's called weight on bit, where you basically use the weight of that machine and you push against it as you're drilling down. But on Mars, the weight is just 1/3. So you actually have lesser force to kind of, push downwards towards. And then obviously there's the power limitations that are involved with Mars being further away from the sun than Earth is. So the amount of heat that is available to charge up your solar panels are also limited. So there are all these different challenges that are involved with drilling, and you're not just drilling and then bringing your drill back. This drill actually has a infrared spectrometer inside it, built integrated into the drill. So as it is drilling, it can actually look at the borehole that has been formed by the drill and do look at some of these hydrated minerals that might be existing there, some water-based minerals that are there. So it has all of these challenging tools. So we are really looking forward to this mission. It's been closely followed. It's been tested in several analog environments as well. And it has similar objectives to what were there with the Perseverance rover. It's also looking for signs of present or past life, signs of subsurface biological activity. So that was all about surface missions. I'll talk a little bit about some of these other exciting and successful missions, which are not landing on the surface, but are actually either flyby or orbiting, depending on which place it was going. So Cassini is both a flyby and an orbiter. I've actually placed a small video that actually shows over a period of, I think, from 2004 all the way to 2017, so 13 years of operations that it was doing. It was studying, it was primarily a Saturn probe, and it also obviously looked at the moons of Saturn, and it made, I think it was adjudged as a mission of firsts. It was one of the most successful missions to fly, and it had a fair share of astrobiology objectives that were attached to it. Similar share of suite of experiments from spectrometers, imaging systems. It also had a dust analyzer where it was capturing dust and actually analyzing them as well. And some of the main findings that actually came out from this probe, in fact, and one of the most exciting ones for the icy moon community, was that it actually confirmed the presence of liquid subsurface oceans, and specifically for Enceladus. And it also found signatures of that indicated the presence of prebiotic chemistry compounds that perhaps showed us that some of the essential elements, the carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, these elements were present. And the presence of hydrogen, it found these plumes that were coming out from the cracks. So they call these tiger stripes. So if you ever have a look at, I think I have an image of Enceladus here. You find these cracks. They're not visible in this particular image, but on the bottom one, you see these plumes that are coming out. So from the cracks that are there inside the ice, you have plumes of ice that are flowing out. And Dr. Jain already spoke about, I think, what is actually happening there. So I won't go into detail, but it confirmed the presence of hydrogen and indicated hydrothermal activity, perhaps on the bottom of these subsurface oceans. And just like on Earth, we have hydrothermal activity that sustains biological activity. That just immediately brought up the tremendous opportunity of life on Enceladus, and also some of the other moons that Saturn has. In terms of Titan, which is a completely different world, here is an image on the top right of the Titan surface that was actually captured by the Huygens lander. So Huygens was the European lander part of the mission that actually slowly, with the help of parachutes, landed onto a surface. It was expecting to land on a liquid body, but it landed on the surface. But even with that, with the little amount of time that it was active, it actually showed us what exactly was there. We did not know much about, because Titan is always covered with dense clouds. You can't see the surface, but with the ability to go down into the atmosphere, through the atmosphere and onto the surface, we were able to actually see. They confirmed that there was this active hydrocarbon-based weather cycle that was present in terms of clouds. There was rain happening. There were these lakes and rivers and larger, you can say not water, but methane-based bodies that existed at these really, really frigid temperatures. And that opened up another opportunity of trying to understand if life could perhaps be not Earth-like, it would be something else. And some of the other findings, which are not directly astrobiology, but perhaps linked in many ways, is the fact that this Cassini mission, it discovered more moons. They actually were able to capture how the ring of Saturn evolves over time, and how perhaps some of the ring elements form a moon. And it also found this really exciting hexagon. I don't know how many of you have seen it. It's not directly related to astrobiology, but I find it extremely exciting. The fact that there's this large vortex on the southern pole of Saturn that is in the form of a hexagon. And many people ask, why is it a hexagon? Why couldn't it just be a pentagon? And these are open questions. So the point here is that there are all these alien weather processes that exist that completely are outside our understanding right now. And we're trying to visit these places with a very faint understanding of a particular form of life that we know it here on Earth, but it is impacted by all of these different parameters that we're still coming to understand. This image that you see was taken by Cassini, and there's a time-lapse video that has been created that actually shows the difference in this particular hexagon vortex in 2013 and 2017. You can see the change in color. So there are all these different parameters that are not even being, put into our equation when we're trying to look for life. And this is just to bring out the challenges of these complex worlds that are out there. And we've seen how Saturn has influenced the formation of moons, and for example, Enceladus. So it's important for us to understand how these host planets that have these moons around them also work. On to Hayabusa very quickly. So Hayabusa 2, which will be landing, not landing actually, it will be returning samples that it's captured from asteroid Ryugu 162173. So it's a C-type asteroid. It looks something like this. So C-type asteroids are important. They help us understand, they have a lot of organics, ice, and minerals, and it's important for us to study them and analyze them because they will help us understand how did water come to be on Earth, how did organics come to be on Earth. So even though you might not find any organisms on asteroids, they have the essential elements, and in this case, water and organics. And it's important for us to, and these are some of the well-preserved, pristine forms of these essential, you can say, biosignatures that are out there. And Hayabusa is doing something very neat. It's actually, you can see from this video, it actually shoots down a bullet. It moves away. That bullet goes down. It's like an impactor. It hits the asteroid. And because of that impact, you have all of these particles that get, it's like almost like a meteor impact. So you have these fragments coming out from the asteroid surface. And then you have Hayabusa going down and then collecting samples and then bringing it back. So it's doing something that's completely, you can say, technologically complex, and it's doing it far, far away from Earth. The other mission that I'd like to talk about, which was a flyby and an orbiter mission, was Rosetta. So flyby, you can see the image on the lower center is an image of Mars. So that was a selfie that Rosetta took. Let's see if I can move my screen away. So this is Mars in the backdrop. So this is Rosetta taking a selfie while it was going towards the comet 67P. And comets are obviously exciting. Our mascot, course mascot, is also a comet, Dhumketu, here you see on the top right, smiling at us. So comets obviously hold, some of these key essential ingredients, and they orbit around the sun. You always see a tail behind them. So that means that they have some volatiles that are constantly escaping out of them. And Rosetta did an amazing job. It had an orbiter that had several different instruments. It also had a lander that unfortunately did not operate, on the surface as long as we would have liked it to. But it found several things for us. It was able to confirm the presence of amino acid, at least one amino acid. It found these non-volatile molecular organic compounds on the surface in the dust. We were able to understand that comets it has its own processes. It has an atmosphere. It has this dust envelope around it. It can be, the surface can also be quite active because of the movement. You can find trickling of dust and soil. And in fact, that was well encapsulated in this time-lapse video that I'd like to show you. I don't know how many of you have seen it, but I find it extremely fascinating. So this is I think a enthusiast Twitter user who was actually able to put together 25 minutes worth of images together, and you can see it obviously happening a lot faster than it would have actually happened. But you see, it's almost like snowfall taking place. But this is not snowfall. This is basically dust grains that are basically bouncing off the surface. I showed you that image of the comet, which is quite irregular. It's almost dumbbell shaped. and it has these rocky, bouldery, particles on its surface. It also has these fine-grained sands, and you see all of this movement taking place. So I think this was the first step towards understanding what comet surfaces are like, and it looked at the nucleus, it looked at the surface and the environment. So it was a technological and a scientific feat, this particular mission, and it gave us a very good understanding of what comets are like. Coming to another challenge, where to land, and I'll just talk very quickly about this. So one certain discussion that has been taking place. So whenever NASA, for example, or ESA, or any of these missions that are going, when they have to go to the surface, and in this case, Mars is one of the most well-studied, you can say, bodies in our solar system, as we all know. There have been series of missions that have landed on the surface. And because of that knowledge, there are several contenders as landing sites where exactly you would like to go. And there's a long drawn process that is quite, it follows a particular scientific method in ways in which you build a hypothesis, you propose it to NASA, for example, and then they, based on scientific value, ease of the engineering, the logistics, and trying to align it with the current goals, they start ranking the different sites. And it can get, very, very debatable. Many of these things are subjective, where there's a certain lack of information which another group of people can bring out and say that we should not be going there. And at the end of the day, a site gets selected. But in many ways, that does not mean that that particular site, most definitely would inform us better than any other site. It's almost always the lack of a particular kind of evidence that stops us from selecting a particular site. So for example, currently the NASA 2020 mission is actually landing inside a delta. So to be looking at the Jezero crater and the delta. Another site, which is a previous site, in fact, that was visited in Gusev crater, we've actually found these small nodules on the surface. And similar kinds of nodules have been found in hot springs in Chile. So you have these morphological evidence that shows us that around these ancient hot spring sites, perhaps what we're looking at is a product of biological activity. So there's different groups of people who want to go again to Mars and then do more missions. And then there's another group of people who want to actually visit some of the higher latitudes where you go where there is water ice present. So there's all of these different discussions that take place, and that in the end also are a challenge for us, that the more information we have about Mars, for example, it becomes more and more challenging for us to come to a consensus as to where do you want to land. Another challenge is miniaturization. Like I mentioned, many of these instruments are getting better and better. We're able to fit them inside our compact spacecraft requirements. One example here is you see this particular instrument that was flown on the Curiosity rover. And an XRF machine normally in a lab would look something like this. So this transition from something that exists in our lab to something that can be fitted inside a rover or a lander takes time. And for more and more robustness in our measurements, this will be a challenge that will constantly come. I've already talked about space environment, but this is to point out, this is an image that was taken on Mars 2005 and 2007. You're seeing our rover, you're seeing the amount of dust that eventually deposits. So dust can be another environmental challenge for operation as well as our scientific operations. In fact, even for the Apollo missions, and the lunar regolith, in fact, is even more challenging to work with because there's no air in the lunar atmosphere. Most of these regolith particles are still quite sharp and edgy, as compared to Mars and Earth, where because of weathering processes and mainly air, all of these particles tend to get rounded. But on the moon, that's not the case. And that actually leads to a lot of abrasion that takes place as you have different moving parts, either in your spacesuit or the rover or your lander, or any of these components that are exposed to the dust. Over time, they actually break down the materials. So that again becomes a huge challenge. In terms of energy, so the radioisotope thermal generators actually utilize a source of plutonium, for example, in this case for the Mars Science Laboratory and also for the Perseverance rover. But many of the other space agencies do not have access to nuclear powered propulsion that will actually help us. getting through some of those harsh cold nights, as well as giving us a decent amount of power budget to operate. So, and then again, this is something that is radioactive. So once the mission is over, there is a challenge of ensuring that you're able to dispose of the leftover, plutonium that will be emitting all this radiation. So that's another challenge to keep in mind, because most of these astrobiology missions are longer. You need to be on the surface for a longer amount of time to complete all of your experiments. This is another material that I thought I'll present to all of you called aerogel, silica aerogel. So it's one of the lightest solids that you can find. It's like a foam, but if you keep on making a piece of foam as rare as possible, it almost appears to be in the form of a gel. It's like a gel-based solid. And the person that's holding it on the right side, you can actually see their fingers through the material. So that's just about how rare it is. So it's one of the lowest density materials that you can find. And it is used for several different things. One is it's used as a thermal insulation. So because it is so light, it takes up less amount of mass. And then you can obviously use it for thermal insulation. But you can also use it for capturing dust particles. So for example, on the Cassini dust analyzer that I spoke about, while it was flying through this dust field, all of these particles, when they were impacting this aerogel, they were not getting altered because of that high speed at which Cassini is moving. So just try imagining, it's traveling at a few kilometers per second at least, and it is impacting your surface. On most occasions, it will either destroy your surface, or even if it is getting captured in some way, if it's not getting bounced off, it'll probably disintegrate because of the kinetic energy, because of the impact that takes place. But a silica aerogel material offers that porosity and it damps that impact. So whatever comes in actually goes through that material, and you can almost, there'll be some papers you can find on silica aerogel based sample captures, meteoritic or grain sample captures, that the sample is actually slowly slowing down as it is coming inside. It's almost like trying to enter something, a very slimy, gooey material, and then slowly getting stuck inside it. So it's something that is extremely useful for capturing samples. But then the challenge associated with that is, once the samples have been captured inside the aerogel, how do you get them out? And in the case of an onboard analysis, how do you get those samples out from that aerogel for analysis? And even on Earth, once we recovered samples from, I think, stardust, which were captured inside aerogel, it was extremely difficult to ensure that they don't get contaminated, and the silica is not interfering with some of the life detection experiments or the biological signature experiments that need to be done. So this is again a boon for us in terms of what it can do, but it also brings with it its own associated challenges. I spoke about drilling. I spoke about some of the challenges on drilling, which might seem like a very straightforward affair, but especially if you're in an alien environment, drilling through alien surface material in extremely low power mass budgets, it becomes even more difficult to do it. On the top left, you see the Phoenix lander. It's an illustration of the Phoenix lander mission, which had a scoop, and it was able to actually scoop and expose certain ice that was below the regolith. It landed quite high in the latitudes of Mars, so it had these ice deposits close to the surface. And on the lower left, you see a hole that has been drilled by the Curiosity rover mission, and it's obviously helped us understand a lot about the subsurface in that first few inches, trying to find organics in the soil. And on the top right, even though the image is completely cut off, but you can see the drill that is going down to about 2 meters, and it will obviously bring its own challenges. And I've already spoken about some of the challenges with drilling. Another neat way in which you can collect samples is using pneumatics. So while I was at NASA Ames, we explored the possibility of using, you can say, a puff of gas. So you're trying to collect samples on the surface. So you're landing, you see that lander that is on the surface of Mars, and on one of its legs, or in fact on most of its legs, it will be having this hollow tube through which you can actually push out a gas that is, in our case, it was the residual propellant in the thrusters. So once you have landed, you don't need that gas, and it's an inert gas, so you use helium or nitrogen, and then that gas basically comes in contact around that footpad with the regolith, and the regolith only has one way to go, and you basically get it inside that sample container. So you want to use the least amount of moving parts. Drills are complicated, they have a lot of moving parts, things can fail, Whereas in this case, it is mainly a gas of tank with a valve that is opened and shut. So that's the only form of actuation that is there present. So when you're trying to do any operations in space, you want to minimize the amount of moving objects, because the more amount of moving objects you have, the more likelihood of things failing is there. So that is something that is very important to ensure that you're able to do things smartly and making sure that you're not using too much of energy, as well as at the same time reducing risk for that particular mission. But again, it also has its share of disadvantages, because you can't drill down, and if you land on a rocky surface, you're not able to get any samples. But again, it's something that has in fact been proposed and might even be used for a mission. And lastly, I think I will point out the challenge of communication, which is where I brought out the importance of autonomous capabilities, where, for example, the Curiosity rover, it's actually a very well, you can say, placed rover. It has ability to directly communicate with Earth, and it can also use UHF band to communicate with orbiters that are in place. So for example, the Mars Reconnaissance Orbiter plays that role of communication support for any rovers and landers which are there on the surface of Mars. And X-band obviously is a very powerful communication system that uses up a lot more power. But even then, keeping aside the power utilization of these communication systems, if you're further away, for example, Mars or elsewhere, it's going to take at least 20 minutes to get a simple single signal back to you and then relay things back to you. So that actually breaks down many things for us. It wants to ensure that your navigation system, your operations, your health monitoring system, all of your instruments, they have to have inbuilt software code that allows it to operate autonomously. And that's where things become challenging. The more and more autonomous your system is, the more complicated the software is. And not just for the instruments, but like I mentioned, the wheels that are moving the rover back and forth, the cameras, when you're landing on the surface, the thrusting mechanism, braking mechanism. So communication with Earth, with an operator, is extremely, extremely key to the success of a particular mission. So therein lie these different challenges, that bring things together. So that was my very quick summary of many things, but I'd like to again draw you guys back to what are some of the main learnings that I'd really like to have you highlight. We've learned what do we mean by astrobiology experiments on flight missions, at least some missions that I've been able to highlight. I also highlighted some of the different types of astrobiology missions that have been held so far, and I haven't touched upon the new ones. So Dragonfly is an exciting mission that has been selected by NASA. I think just a few days back, it got, postponed by a year. So I think it's probably 2027 or so, if I'm not wrong. So it's actually, again, a mission that will be going on the surface of Titan, and it'll be having a helicopter as well. So it'll actually be hopping and flying around and doing exciting things. And with the recent finding of, phosphine gas on the Venus cloud environment, it might even, push some of the Venus missions to, in fact, incorporate some of these findings and strengthen itself in one instrument area as compared to the other. So there might even be a reselection of instrumentation suite for many of these missions that might be coming along. And of course, many of the findings that we find here on Earth, our own stromatolite records, our oldest life that we're finding here on Earth, every few years, there are different papers, strong papers that come out. In fact, if you're looking at Mars, we recently found, these active liquid water bodies in the subsurface of Mars. So there are all these different things that actually help us improve our mission profile. And, you're always working towards ensuring that whatever you're detecting, you're able to do it confidently, because these are expensive missions and they have to be thought through and have as large of a, you can say, consensus in the scientific community, because you might be doing a finding and the instrument might be operating really well. You might have achieved all of those things. But if you're not fulfilling that criteria, like the one that I mentioned, and sufficiently demonstrating the ability of your instrument to rule out abiotic signatures, many of those things, again, are left open-ended. And that in many ways can jeopardize a future mission from any other space agency or even from your own to that particular body. And the focus can shift to another place. And you might again have to start from scratch. especially in the case of Venus, where Venus was being substantially well explored in the late 70s and early 80s. But because of many political reasons, you know, a lot of information that was archived in the Venera missions, the initial Venus missions, is in fact lost. And many of that exploration discoveries and observation and measurements had not been archived, and even if they were archived, they were not completely well translated and, you know, put forward to the community. So that is what is at stake when there is an ongoing momentum for a particular planet's exploration. You want to ensure that you are well informed, your experiments are well designed, and are able to complete those different tasks. So with that, I will end, and the next class will be on planetary protection and space policy. That will be moderated by Dr. Afshin Khan and Dr. Alyssa Hadaji from Harvard Law School. And that's about it. With that, I will take some questions. I'm happy to just scroll through some of these questions. I see a lot of them have been answered. So thanks a lot to the other instructors for taking that. Okay, let's see, what do we have here? So the question is, what type of, question from Prajakta, what type of mechanical stresses they experience while launching? And is there any automated system to handle that stress or not? So that's a good question. Yes, so normally whenever you design a particular system, it has to undergo vibration tests. So rather than actively dampening out those stresses, you want to ensure that your system by itself can already handle, it's well packed, you know, it doesn't have any objects that are loose, and that are mounted in a certain way to ensure that there isn't any additional stresses that can, you know, be encountered. So you have these shaker tables. If you read about spacecraft qualification tests, you'll find it's quite standardized for most space missions, where you basically mount your particular spacecraft or your, you know, so testing takes place at different levels. First, your instrument has to undergo that test. Then it is integrated inside a subsystem. That could be your, you know, your science payload or your science package that undergoes that test. And then everything is integrated into the larger spacecraft, and then everything else, you know, has to undergo those tests. So at several different levels, you have to accomplish and complete certain vibration qualification requirements. And these are normally different frequencies with which your hardware is shook, basically. So you basically do it in all the three different, you know, axes. You do it horizontally, vertically, you turn it around as well. So depending on what your profile is, you follow that profile and then you do that. There isn't an automated system to handle these stresses, but you definitely have passive ways in which you can damp them. So you have dampeners, you have any kind of vibration damping. Mostly it's a soft material that kind of goes around and ensure that even if there's any additional amount of, you know, whenever there's a stage, whenever you launch from the surface of Earth, there are these different stages with which the rocket launches. And then whenever one stage gets over, you have this jolt that takes place. So, and then also when you're in space, you've approached your target world and you're trying to come to a particular point and do that braking. So you want to make sure that at all these different stages, your system is well equipped to handle those stresses. Is it possible to use CubeSats in place of huge rovers? Okay, so the question is from Nitya. Is it possible to use CubeSats in place of huge rovers to land on the particular planetary body of interest? These CubeSats can be launched from ISS and will go from a single or maximum two purpose, like one CubeSat launch only to get sample from Mars, or a CubeSat especially to get images, and after their work will come back. From ISS, it would be easy to get back those samples to Earth. This can help to cope with the general challenges faced by. Yes, so good question, Nitya. In fact, the MAVEN mission, if you read about it, it actually carried with it two CubeSat, and they were mainly technology demonstration missions. You cannot replace CubeSats. You cannot replace rovers currently with CubeSats. It's because CubeSats are small spacecraft. They are good for achieving things within the amount of power systems and communication systems that they have. So for right now, yes, things are changing. We are seeing a lot of different concepts that are being presented of different kinds of CubeSats, you know, for the lunar orbit. They've also been talking about CubeSats to go out towards Venus, you know, independent CubeSat missions to go towards Mars. But the main challenge that is faced is in the power and the communications. So most of these systems that are flying away from us require really powerful communication systems, most likely X-band form of communication systems that require large, transceivers that will allow us to transmit as well as receive signals to do that. And then again, from that CubeSat, if you're trying to eject something to come out and then go onto the surface, and then if you're trying to, because you mentioned substituting rovers, so I'm guessing you want some part of that CubeSat to also go and land on the surface of Mars, for example. It just increases the amount of complexity. So you can use CubeSats in many smart ways. And actually, I encourage many students who are part of this lecture series to investigate as many ways in which CubeSat components can replace some of the larger, more expensive components of these planetary missions. That will go a long way in bringing down the cost and the complexity of these missions. But you cannot just completely replace a rover with a CubeSat. It has to be done component-wise. So you can find certain components of cameras or spectrometers or small energy storage systems that are used on CubeSats that could perhaps be replaced on planetary spacecraft that are going towards it. So we're not there quite yet, but it's definitely something that we'd like to work towards. Okay. Does the CMB possess the ability to hinder the trajectory of a satellite? I'm not quite sure what CMB stands for. Tane, if you could just clarify it in the chat box. Why plumes are visible in single pole in Enceladus? Good question, Krishnendu. I do not know the answer to that. Jen, Afshin, Michael, anybody of you would know? Why do we only see plumes on one pole of Enceladus?
I don't know the answer to that.
I would assume wherever there's surface activity going on whichever side of Enceladus, that's why those plumes are visible on that side. I mean, that's just a straight away.
Mm-hmm. But I don't think they have noticed it on the North Pole. Isn't it that they've only seen it on one pole? They've never really seen it.
Well, I think Afshin's just given a reasonable hypothesis to answer that. And also we're, even though Cassini was observing it, I don't know how many times, 12 times, or maybe, we could have missed things too.
Okay.
So we were lucky to see what we saw, and it's very tantalizing.
Okay, so that's still an open question. We don't know enough, and there are obviously plumes where there are cracks in the ice, and cracks can take place depending on where the orbit is, and we don't even know how long these cracks have been open for. So that's still an open question, Krishnendu.
Yeah, good question, though.
Yeah, good question. Great question. We all wish we knew the answer to that. Arpita asks, what is that point at the center of the polar hexagon of Saturn? Is it called I? Okay, so I'm not sure what it is called, but I'm guessing it is similar to the kind of global vortices that can form in an atmosphere. So it's basically a swirling cloud that is there. And there's definitely some kind of a low pressure formation in the center. But why exactly is it differently colored? I do not know. And I think not many people know that. These are just observations. We haven't been there long enough and looked at that particular point long enough to know more. Please, others who are much more knowledgeable in some of these questions, please feel free to jump in. I do not want to be the authority on many of these things. How does, Ritik asks, how does the asteroids influence the experiencing of watching Jupiter, Saturn, Uranus, Neptune from Earth? Why can't we see any disturbances due to asteroids? The experience of watching. So asteroids are smaller objects. They definitely have their own influence, but collectively we don't see them having the same kind of influence that a body like a moon or a planet would have. They definitely can get in the way when you're trying to observe these different planets from Earth. But aside from that, and many of these asteroids are actually not even lit. They're actually dark because they're not large enough to reflect the kind of sunlight that a planet or a large moon could reflect off. If it's a moon, for example, it's reflecting the light that is coming off. You can see the moons of Jupiter from Earth. You can see it with a good binocular. And that's also because it's reflecting the light that's coming off the planet next to it, in this case, Jupiter. But many of these asteroids, I don't see ways in which it could, I don't understand. You mean influence the experience of watching? Do you mean, do they visually obstruct us? That is not the case. Okay, Kawaljit asks, what materials are exactly used for the spacecraft building, as we need one which can survive all the difficulties as mentioned? So that's a great question. And yes, there are a list of commonly used material that are used for spacecraft building. So for the structure, you almost always use some form of aluminum or a titanium or a reinforced polymer, that can withstand, again, depending on what you're talking about. If it's the structure of a rover or a spacecraft, it is a metal, and aluminum is used a lot because it is having, the highest strength, one of the highest strength to weight ratios. It is also cheap and easy to work with. You can mold it in different ways. You can manufacture, ways in different ways. The thermal properties, the physical properties of the material is well understood. So aluminum is used, just like in aircraft, you have aluminum that is used. You have the same use there for the structure. In terms of some of the other materials, you basically have to, your material has to fulfill certain criteria. For example, the temperature variations. It needs to be able to operate at low temperatures and at high temperatures. So you normally use a lot of thermal insulation material. So I don't know if you are familiar with, just like you have aluminum foil that you might have seen at home, that you must have used at home to wrap food in. You have these really, really thin aluminum foil material that is normally plated with a very highly reflective coating. So either a gold or a silver foil. And you basically crumple up that sheet of aluminum. So it's really, really thin. So a quarter of a millimeter thin. And that's called multi-layered insulation. You basically wrap your entire spacecraft. That's why you must have seen a lot of images where your spacecraft is gift wrapped. It looks like a massive gift, right? So that material is actually used to ensure that the rover is not losing heat when it is in space. And if there's any heat that is impacting from the outside, it is getting reflected off as well. So you have different materials for different purposes that are used. And then, like I also spoke about aerogel and some of those other kind of materials as well in my talk. Okay, Nasrullah asks, is there any difference of life in a planet and life in a moon of any planet? Sometimes we see in case of Saturn, the planet is, in the case of Saturn's, the planet is a hostile place for life, but its moon like Enceladus, Titan are very much potential area for ancient life. So is there any difference or effect for life on planets and life in moons? That's an interesting question. I think what you're trying to get at is, does the planet have an influence on whether that life is there on moon or not? And in that case, yes. So for Enceladus, and even for that matter, Titan or some of the other icy moons, they are influenced by the gravity, the thermal, reflections coming off from the moon, and that gravity and that thermal environment, for example, definitely does affect how that moon has come to be. The fact that it has a subsurface liquid water ocean is affected by the fact that it has something that is influencing the gravity of that particular moon. And in the case of Enceladus, we have seen that because of the variation of gravity, the ice has constantly been at friction, and you have this tidal heating, which causes this warmth that ensures that there's a constantly liquid water body underneath it. And we haven't really seen anything like that. So the way a moon is built and the way a moon is formed and the way a planet is formed is obviously also different. So it can lead to different forms of life as well. That's a good question. Okay, so Vishnu asks, as Sid just mentioned, how are the radioactive waste after the end of mission disposed or handled at current time? And are there newer evolution of these mechanisms going ahead? So that's again a good question, Vishnu. Currently, with any missions that go, complete, they reach their end of life, there's sufficient amount of reinforcement that is there around the particular radiation source. And over a period of time, we have seen this with, in fact, if you remember, if you've seen the movie The Martian, you can actually see Matt Damon actually going and digging out a rover and then trying to pull out and then you can see it has these radiation signs all around it. So currently there's no, it's not being disposed as well as you could do it if it was on Earth, but they ensure, and that's where it gets really, really expensive and cumbersome to fly any form of radiation source into space, where you have to ensure that your system is completely leak proof and you are ensuring that you're not contaminating or jeopardizing the lives of future astronauts or other missions that are going onto the surface. So it's normally just solid reinforcement around the systems that prevent any kind of leak. So Chirag asks, is it possible, like as we introduced them with UV and laser, they got mutated anyway, and then by having favorable environment, they started building life blocks in cells? I will try to answer this question and hopefully somebody else can help me out. I think what you're trying to understand is, if there's an external influence in the form of your instrument, when you're trying to measure something, it will definitely alter your target sample that you're looking at it. That is definitely a possibility, yes, for sure, which is why it becomes even more important to completely understand the rate of influence of these external parameters, where you're trying to shoot UV or where you're trying to shoot lasers for that matter, or heat something for that matter. You might be altering that particular sample. But whether they can start building life blocks in cells, I don't think we're doing that measurement for that duration for something to start or instigate something. I don't think that is something that is much of a concern. Okay. How can any element can be detected if any substance or elements undiscovered in Earth? We can't say that we haven't found all the elements of the universe. If any inert gases used for sample collection react with any elements of planet, unfortunately, how can you measure that? So that's a good point. So again, we are in the realm of uncertainty with that. If we do come across, so as far as our understanding of our physics chemistry on Earth, we've been able to classify and identify the different kinds of elements that we have. And we definitely use inert gases because we want to ensure that those gases do not react with any of the known form of elements that we have. But if there is something that we do not have a complete understanding with, it will most likely give a result which could be a false positive or a false negative, and we will not be able to know for sure. But the signature of that particular element will also be unique, and perhaps that might be one way to tell us that whatever we're looking at is something which we completely do not understand, and there'll be scope of ambiguity, which will perhaps lead to a non-consensus, but at the same time might lead to a significant discovery that you have found something that doesn't exist on Earth. What instrument are you most looking forward to seeing exercised on future interplanetary missions? So I'm an engineering person this is a question from Lisa, who is excited about drills. I'm excited about the subsurface, and I'm really, really looking forward to the ExoMars mission, the Rosalind Franklin mission in 2022, and its ability to drill down and have integrated sensors that can actually look at some of the subsurface stratigraphy, look at the minerals around it, and do that kind of analysis. Because in my mind, that would be an exciting thing to do from a Mars perspective, and the ability to drill and look at samples on the subsurface would be exciting, even if you're looking at icy moons for that matter. So that's something personally I'm interested in.
So do you mean like instruments in the borehole itself?
That's right.
Yeah, I think that's good.
Yeah. Another question from Nasrullah. Siddharth said that due to time lagging of communication between other planet and Earth, everything should be automated, or automated set of equipment. How can they communicate between the equipments of rovers? So just to clarify, there is a extent of automation. Obviously, there's a lot of manual control. In fact, there are drivers of rovers, in fact, who are classified, and probably Afshin and Jen would know more about these people, who actually have that job of driving around rovers themselves. So you can't autonomously navigate. It is being controlled by us. A lot of things, in fact, are being done by us. So there's a certain degree of automation that is in place. So it's not to say that everything has to be automated. How do they communicate between equipments? So again, depends on from mission to mission. On many occasions, they do not communicate the different equipment amongst each other, the different instruments for that matter. But on many occasions, yes, you will have an integrated system where, for example, the mast cam will be sending its readings to the spectrometer that will be looking at the data that is coming back from it. So all of that is completely built and tested on ground before it is sent out. So there is a degree of automation and there is a degree of communication between the different systems as well that is built in. Okay, CMB means cosmic microwave background. Okay, thanks for clarifying that. I'm just gonna scroll up to your question. Okay, so does the cosmic microwave background possess the ability to hinder the trajectory of a satellite? To hinder the trajectory of a satellite? I don't think so. I do not think it has a sufficient amount of energy. I think gravity perhaps would do a lot more than the cosmic microwave background. I'm not an astrophysicist, but that's as far as I understand, it wouldn't do anything.
Yeah, I don't know the answer to that one.
Okay. But it's always good to think about these external influences, which we do not take into account. There might be these external influences from outside our sphere that we're looking at. Why can't thermal barrier, question from Satya, why can't thermal barrier coatings used instead for insulation? Is there a specific reason? So you can use thermal barrier coatings. One thing that tends to happen when you go into space is called outgassing, where if you ever try to heat something up, you'll find that it becomes volatile and things start evaporating from the surface. So similar thing happens when you put a material that has a high outgassing coefficient if you put it in a vacuum environment. And we do these tests on Earth. We have these vacuum chambers where basically there are these hollow tanks and we have a air inlet or an outlet. And then mostly it's an outlet, it's a pump that is basically drawing out the Earth's atmosphere that is inside this particular tank. So you use a pump, you bring out everything and it's suddenly a vacuum, right? And you can achieve different levels of vacuum, whether you want to do it for Mars or whether you want to do it for a space vacuum, you can achieve different amounts of vacuums. And then what we normally see is that because of this vacuum environment, anything that is there on the surface can erode. So there are certain materials that are having lower outgassing materials and some that are having higher outgassing materials. And on many occasions, we have seen these thermal coatings that are normally used on Earth. They are not as effective because as soon as they're put in that vacuum environment, all of that material just outgasses and comes off the surface and there is no thermal barrier coating. So you have these specific materials that are used. Like I mentioned, you have these, aluminum foils that are made in the form of different layers. So it's called multi-layer insulation. You have specific materials that can withstand like aerogel, like I mentioned, also ceramics that are used that can withstand high and low temperatures. And yeah, I think that's to answer that question about why don't we use something that is coating. There are certain kinds of coatings that are used, but the regular thermal barrier coatings that I think you're talking about cannot be directly applied there. How much debris do we contribute to the space due to the activities that we conduct? Question from Neha. Again, an excellent question. So yes, we are creating debris, not just in orbit, but we're also creating debris on different planets. No denying that. But if you are heading out, maybe Afshin, I see you've unmuted yourself. You want to answer that? Afshin?
Oh no, I'm sorry. No, that's something. It was just left on mute.
Oh, okay.
No, but actually,
no, go ahead. Sorry.
That's a really good question, though. How do we address space debris? And there are people working on that actively. I thought I answered the one from Neha about what happens to the rovers when they stop working on a planet. Well, we just leave them there. So it's essentially, I've seen cartoons that say Mars is a robot graveyard.
Yeah.
He has one active rover right now, and everything else is just, a dead rover or dead robot. No, but space debris is a serious thing. In fact, I don't know if you guys all heard in the news that was it yesterday or 2 days ago that the astronauts on the ISS had to take care and get up in the middle of the night because there was a leak that was caused by some debris from an old Russian craft, I think. Anyway, so it's dangerous for future missions. It's dangerous for satellites, and there are sort of ideas of how to collect it. But as far as I know, and there are actually startup companies that are targeting the collection of space garbage. But I don't know of any that are active at this point. Do you, Sid?
Mm-hmm. Sorry, what did you say?
I don't know of any that are active at this point. They're
Oh, no, no, they just done a lot of, yeah.
There's, I think JAXA has a plan to have a dedicated mission to get rid of or take care of some of this lower Earth space debris along with ESA, in collaboration with ESA.
Yeah. Well, and
yeah,
that's and then there are people who track space debris, and then there are the military that track classified space debris, which is probably another factor of 2 to the other space debris. So
yeah,
I think when I was paying attention, and this was a few years ago, there were over 28,000 items that were being tracked, and an equal number being tracked by the U.S. military. So they were not in that first inventory. So it's a growing problem. So that's a good question.
And that's I think that's a great thing to think about. This is all about responsibility. Whenever we're sending up anything, it's not just about ensuring that it's clean, but also ensuring that it will not decompose, obviously, right? Because it's going out there, it will remain as long as eternity, unless it comes back. If it's an orbit, it will probably deorbit and then come back and burn, which is normally what is done. So on many occasions, you have missions which have a lifetime, and then after that, it is just brought down slowly and slowly, and it just comes into the Earth's atmosphere and it burns. But for anything that is heading out further into space, there are less ways in which you can decompose or complete those missions. So that is something that it's part of our exploration. We try to send up things which will not leave a lot of debris. It'll just probably be single, placed in one place. And then perhaps in the future, there would be ways in which we could scrap all of that material. But right now, no, there's no way to do it.
Well, there was the Skylab in the 1970s, which was sort of the first space station. Mm-hmm. And then its orbit was decaying, and eventually funding went away. And so they let it come down to Earth. And they asked people to send debris back to NASA.
Yeah.
Now, most of it went into the ocean, but they did receive parts, or at least postcards about parts retrieved on all continents. So that was a little scary, interesting.
Mm-hmm. Thank you. Thanks, Jen. Question from Neetu. Recently, there has been evidence of subsurface or underground water on Mars. Could Perseverance rover be moved from Jezero crater to this place on Mars and collect data on the same as the possibility of finding life that would be more over there, right? So I think these lakes are at least 1 kilometer deep, and Perseverance doesn't have a drill that can go down that deep.
Well, no, that's, what, wouldn't it be great if it could do that, right? I mean,
yeah.
Jezero crater is, I don't know how many kilometers from the polar area where they found now 3 lakes. Mm-hmm. And you mentioned as shallow as 1 kilometer. Now Perseverance is going to have a drill that'll get down to 2 meters, I think. Is that right? Or but anyway.
That's the ExoMars rover, Jen. I don't think the Perseverance.
Only 1 meter. Anyway, they do have something called a ground penetrating radar.
Yes, that is true.
So that would probably be able to characterize that lake or the water under the surface. It would take some time, but right now it's focused on Jezero.
Yeah, and then there's so many things that go into the mission, that you cannot change because of a particular finding, even though you'd be attracted towards it. But there's also the engineering side of things. Whenever you decide a particular target location where you want to land, all of these things are taken into account. So there's less chances that, in fact, almost no chances that Perseverance will go there, but perhaps in the future, we might be having a mission that goes there. Okay, Satya asks, Canadarms are used for various operations relating to the payload. When rovers include various complexities, can a similar robotic arm be used? Yes, it can be used. In fact, the Phoenix lander that was in 2008 that landed on the surface of Mars in 2008 had a robotic arm, a scoop that was actually scooping up and bringing things inside. And these are exciting things. The reason why we don't see a lot of use of it is they're heavy. They take up a lot of energy, especially, Canadarm operates in low Earth orbit in our space. So your budget is very different. Your power energy budget is very different. Whereas something that's operating on another surface, you're more than likely to use the weight of your rover to drill down and bring samples up than use a scoop. Even though, having said that, it's not something that is disregarded. It is something that robotic arms are, in fact, very useful, depending on what you're really doing and how exactly your instrument is placed to receive the sample. Sahaj Bandwal asks, and probably a question for, I don't know, maybe Jen or Michael or someone. Why was Oxyaplanum selected as the landing site for the Rosalind Franklin rover?
ESA selected that site.
Was there
there was a scientific panel. There's Dr. Stuart Turner and Dr. Peter Forden, who both work at the OU, were part of that panel. And I got to see some of their slides for the argument. So it was between Oxyaplanum and another site, the location of which completely escapes me, if anybody else remembers where that was. So there's two key factors. There's the science question and there's the engineering factor. And the engineering factor was, it had to be at a specific point on the planet so that the rover had sufficient time to slow on its descent, because the previous ESA rover did not slow on its descent.
Yeah.
And they wanted to maximize chances that it would actually reach the surface at the correct speed. And then the science question was, they were looking for environments that had evidence of previous water interaction. I believe there's evidence of former deltas at the Oxyaplanum site, but it was very hotly debated where it would land. But it was immediately restricted from this engineering question of where will the angle of entry be correct?
Yeah. And that's obviously, like I mentioned, extremely challenging trying to soft land on other surface. We've had unfortunate incidents where, even for that matter, the ExoMars first lander was not able to do that. So I can kind of understand the balance tilting towards the engineering side a little more, where they want to ensure that it's done at a site where it's able to enter at that particular velocity. Thanks a lot, Michael. Question from Astrid. Could the velocity objects have, when arriving on a surface body, be used in advantage for collecting soil samples? That's a good question. Yes, perhaps. It hasn't been used so far. You could perhaps shoot an impactor that lands before your main body arrives, and that impactor creates a debris of cloud that is kind of moving up, and then you collect it. But it might not be the velocity with which you're arriving, because that's actually very high. So you definitely want to slow down to a certain extent, because you have to, you have to get into the orbit of that particular, you have to get inserted inside the orbit of that particular body. So, but obviously, even if you're in orbit, it's still a component of the same velocity with which you have traveled. And, this has been done, like I showed you the Hayabusa mission, where it shot that little impactor and then had that cloud that came up and was captured. And I think the L-Cross mission as well does that, where it shot an impactor and then there was a cloud that was eventually captured. So it is possible, but then again, really depends on what exactly are you looking for, and to what depth do you need to, what kind of a depth of impact you need to create to have the samples being blown up. And then again, like I mentioned, there could be alteration. Life detection experiments are tricky, they're hard. Any exposure to high energy environments could in fact be deteriorating or altering your samples, and what you're looking at could not be a natural environment. It could be something that's been affected by your experiment. So it's not easy, it's not that straightforward. Okay, so Nasrullah, can you explain about the MOXIE experiment of perseverance in terms of chemical experiment? This is the experiment that is that's demonstrating the ability to produce oxygen. I think it's a group in MIT. Jen, do you know a little bit about the MOXIE experiment?
Actually, not very much. I would refer Nasrullah to the web.
Yes, I think
I could jump in, just give a brief overview. So yeah, this was developed at JPL to demonstrate the, so MOXIE stands for, just for others who want to know, the Mars Oxygen In Situ Resource Utilization Experiment. And this is to produce oxygen from the Martian atmosphere, which is mostly carbon dioxide, electrochemically. So what it's going to do is do some electrochemical reactions to capture that carbon dioxide and then produce oxygen and carbon monoxide. This is basically to demonstrate future human missions where we are trying to show that we will be able to make oxygen on the Martian surface for you to be used by human astronauts or whatnot.
Great, thanks a lot, Afshin.
Very exciting. Very exciting that, I mean, it's actually a really exciting instrument.
I think this is the first time that we're trying to produce oxygen on another planet.
Yeah.
Never done it before. So again,
so we've characterized, or Curiosity has been characterizing the local radiation environment. With the idea is, you know, how does the radiation change on the surface of Mars, and how would that impact future humans on Mars?
Yeah.
So now with MOXIE, it's like, how are we going to make air for them to breathe? That's pretty cool.
Great. All right.
So yeah, all great questions, but I see that we have kind of crossed the 90 minutes window. So it's up to Siddharth. If you want to continue, or we can take these questions offline and they can be answered at a later time.
I think there are just 2 or 3 questions. I'll just probably end them very quickly, if you all don't mind. So someone's asked me about resources. I will definitely try to upload some material that will help students understand the engineering challenges. There's a book called Space Mission Analysis and Design. It's like our Bible book for the space engineers. So if you can find a open access copy of that, please do go through it. Or if your local library has it, that'd be great. And also there's a lot of papers depending on the mission that are published by the engineering team. So these are great resources. Thoughts on Starman and private space companies launching various objects into space, as well as non-essential payloads. Again, it's a very personal question depending on who you ask. Some will say that it's Elon Musk's company, it's his money, it's his way of doing things. He's not doing it with taxpayers' money, so he can do whatever he wants. And there's the other group of people who would argue that, well, we could have sent so many different instruments on it and done things. There is no right or wrong answer. If you would like to know my personal opinion, I feel there could have been a little more instruments on that car, something that was fitted on Starman as well, that would have added value, but then I don't have a strong ground because it's his money, it's a private company, he's welcome to do what he would like. Neha asked me a couple of conspiracy theory questions. Look, Neha, yes, there have been a lot of discussion about different kinds of unexplained footages, and that's what they are unexplained. For anyone to claim that they are aliens or advanced life, there isn't sufficient fact-based knowledge towards that. So UFOs remain UFOs as long as they're unidentified. Once they get identified, they become FOs. So that's our stand on it. Can rovers claim an exclusive area of study on the surface of Mars? I don't think they can claim any area. In fact, if you're landing on another body, you cannot claim onto any particular region, territory. It's all international territory. It's open to any and everyone. And there are rules that are now being laid down. You should read about the Artemis Accord that NASA is now spearheading, that will kind of put together some kind of a guideline to ensure that for the lunar South Pole environment or the lunar surface environment, there's responsible and communicative exploration, inclusive exploration that is taking place. And thank you, George, for attending my talk. I think, and thanks a lot to the instructors for answering all of these questions. In fact, they've answered more questions than I have. So thank you so much for that. So we are way over time. I would really like to thank everybody on this panel, as well as the students who have joined in across different time zones to be with us. I again want to send out a reminder for the analog site assessment task. These are important for us to understand how many of you are actively engaging in this course. I think over 200 people have done it, which I think is great, but we have about 640 people who have signed up for this course. So let's see as many as we can, and that will help us give out the certificates. There'll also be a feedback form that will be circulated that will help me know how well I did and improve us for our next course, as well as the glossary. So if you've heard some exciting words, make sure you fill those out as well. So with that, we will wrap up and see you all next week. I might not be there. I'm probably going to be traveling, but Afshin has agreed to moderate the panel for us. So thank you very much, and see you all. Thank you so much, and see you all next week. And I hope IT please stop recording.